Hello, am I audible?
Yes, sir.
Audible to everyone? All right, let's start then. I guess we will start. So I'll just tell you the agenda for today. So today, basically, we will divide the entire class into two halves. We will have a class from now, which is 8 p.m. to 9 p.m. And then at around 9 p.m., we will have a 15 to 20 minutes break. And this break is primarily because I have a meeting with my manager. So there is a customer issue that came up today morning. So we have an emergency meeting which I need to attend at any cost. So, but it will get over in 15-20 minutes. It won't last more than that. And then after that, we will start and let's say 9:20 p.m. and we will continue till whatever, like till we cover enough for the day, like whatever I have in my mind. Okay. Sounds good to everyone? So, did you guys get a chance to try the question that I gave you? Was anyone able to solve it? You were able to code it yourself, both the questions? Do you want me to code it? Let's code it, and then I'll show you what are the modifications that need to be made, and we will take it from there. What about others? Everyone, did you guys get a chance to try it? Ayush, did you give it a try? Akshay, did you give it a try? Gaurav, Karan, what about it? You tried? Nirav, did you try? Pravalika, Ritik, Sai, Savio? Okay, but it was not getting accepted. I'm talking about the questions that I gave in the class itself, like yesterday's class. They are the same basically. On Lead Code also, they were the same questions that I posted, pretty much. Okay, I will then do it once and we will make changes to it. So this is the question that we were doing, right? So if you remember, I will just recapitulate what we have done so far. Can someone take the honors of recapitulating what we have covered so far? Uh, Let me pick up someone. Tanya, can you recapitulate what we covered yesterday?
Yes, sir. So we basically first talked about what recursion was, like what are the different ways to look at recursion. Then like we looked at how function calling works in general and how function calling happens in recursion, like with respect to the stack and like memory allocation and deallocation.
Right.
Then like we looked at basically the vocabulary, like the base case and the recursive definition thing. And then we looked at the template to solve a problem using recursion. So you have like 5 steps in that, and then like we did the questions. Like we
Yeah.
did one question for the template.
Yeah. So if you remember, the template that we were discussing yesterday, with respect to this question, we said that we could do it using two types of decisions. So the question is, just for the interest of everyone, you have an array of numbers and assume that there are no duplicates in this array for now. And you have a sum. You can pick a number any number of times and you have to find out all possible subsets of this array which sum up to this particular value. That's the question that was given. So if you remember, we outlined the following steps to solve any particular recursion. we said that the first step would obviously be to represent the particular problem. So how do you define the problem mathematically? That's the first step of solving any recursive problem. And here we said that the problem that we have is basically defined by two quantities here, our array and the sum that we want to make. Then we said that after you are done with representing the problem, you have to make a decision. So this decision is probably the most important part of coming up with a recursive formulation. And we said that in this case, generally when you are deciding something, you look at the eventual solution and you look at how you arrived at that eventual solution, or you look at the pattern in the eventual solution that you have. So in this case, we said that look at one possible decision was that look at all possible subsets that can come from this with sum up to sum. So in all these subsets, basically we could divide it into two categories. One category of subsets does not contain two at all. And then there is another category of subsets which contain two. Right? That's what we said. So this is the decision that we made looking at the eventual solution. And from there, we came to step 3, wherein we defined our subproblem. So our subproblem in this case, we said that our subproblem, if we have basically two cases, if we consider 2 or if we don't consider 2. So if we exclude 2, then our subproblem is basically finding the sum in this half of the array. All possible subsets which give a sum of sum in this particular half of the array will be my subproblem. So A1 to n-1 will be my subproblem with the given sum. And if I include it, then my sum basically, then my subproblem boils down to finding sum minus A0 in this half of the array, the entire array again. So we said that then the subproblem reduces to sum minus A0 and A0 to n-1. This is how we defined our subproblem based on the decision that we are taking at this point in time. And after that, we said that once you have a subproblem definition in place, what you will do is you will basically come up with a mission statement. So our basic mission statement, there are two parts to this. First is coming up with a function prototype, and then defining the mission statement in English. So here we said that our function prototype, whenever we are defining, will basically comprise of all the parameters of this particular subproblem that we have. So what are the parameters? You have an integer which you can represent by some variable, some integer variable, and then you have a suffix array which you have to represent. So then we went about talking how do you go about representing a suffix array. We said that a suffix array can basically be represented by the array and the starting index of that suffix array. So with this, you will be able to encode a suffix array, and this integer variable will be able to give you a representation for this sum. So from there, we said that our function arguments will basically comprise of these 3 variables. And we said now then basically the mission statement in English for this particular function comes down to that FAI sum will give me all subsets with sum equals to sum for array A I to n-1. And that's how we defined our mission statement. And once we have a mission statement, what we said was then we go ahead and write the recurrence relation. And we said that recurrence relation is nothing but the relationship between the problem and the subproblems. So we said that our recurrence relation is nothing but FAI, AI and sum is nothing but you take the union of either you exclude it. If you are excluding it, then you have FAI plus 1 comma sum. This will give you all possible subsets without AI. And then you will take all possible subsets, including AI, for which this is the subproblem. And for every such subset that you get from this particular this particular function, you will append AI to it. So this is how we came up with the recurrence relation. And then this is 3B. And then we finally said that, okay, now that you have a recurrence relation, just write down the base cases. And we said that base cases for us in this situation, in general, base cases will be of two types: positive base cases and negative base cases. Positive base cases are cases which give us a result, and negative base cases are cases which do not give us a result. So generally, whenever you want to write a base case, you have to think about all the varying quantities in your recursive formulation. So here, what are the varying quantities? I and sum, correct? So from here, we will define our base cases. And we said that the positive base case will be when sum is 0. So when sum becomes 0, then I have found a particular subset. So basically, when sum is 0, no matter what the array you are left with, you will have the only way you can construct a subset with sum 0 from any given array is that you return an empty subset. So we said that you will return a 2D array comprising of an empty vector. That's basically the base case for positive. And we said that the negative base case is nothing but other quantities. So if one is, the sum can become negative, right? So if the sum becomes negative, you don't have a solution. So one way of representing it is that the solution vector is empty. Here the solution vector had an empty subset, but it did have one element, which was the solution. And the other case is when you reach the when the sum is positive and you reach the end of the array. So when you reach the end of the array, then basically you cannot make, because you basically, the question is that from an empty array, how can you make a positive sum? So there is no possible way you could do it. So you will return an empty array for that also. For sum negative, because all the elements in array are positive, there is no way you could make a negative sum. So again, the result is empty. So two main points in this base case, writing the base cases, is think about all the variables in the recursive formulation. So things that are varying, and think about the smallest possible value for each of these variables, the smallest possible sub problem. And those will typically be your base cases. The other point to keep in mind when you are writing these base cases is that treat them as standalone problems. Don't mix them up with the actual recursive formulation. So you tell yourself that just treat it as an independent problem. What is the problem? The problem is that you have an array with some numbers and you have to make a sum of 0. How many possibilities are there? There is only one possibility, which is the empty subset. So you return that. You don't really have to think about anything else. Similarly, you treat this case as standalone. How many ways can you make a negative sum from any given array? You cannot make a negative sum. So you will basically return an empty result. Similarly, how many ways can you make a positive sum from an empty array? There are no possible ways of doing that as well. So you will return an empty result. So these are the 2 points to keep in mind when you are writing your base cases. And another thing to keep in mind is always write your positive base cases first, followed by your negative base cases. You will get an intuition as to why we are saying this, but this is also one thing that you should keep in mind. Always write your positive base cases first and then the negative base cases. So these are the things to keep in mind when you are writing your base cases. And the other half, the other part, 3 and 2, is basically dependent on the decision that you come up with. So that decision, I gave you 2 types of decisions that we looked at yesterday. One was include, exclude.
Excuse me, just a small doubt.
Yeah,
Can you
sir.
go back?
Yeah, tell me.
This positive negative thing which you just told, that we should write positive base cases before and then the negative base cases. Is this like necessary? I mean, should we keep this in mind, or is it just like good coding practice?
It's necessary. Like, it will impact your correctness sometimes.
I mean, can you explain like how, or a small example?
Yes. So for instance, let's say you are taking this particular case.
Okay.
Let's say, let's say you are, actually, if you are including in this particular case, it will not really matter. Because, yeah, in this particular case, it will not. Let's take up a case. Okay. I will come back to that particular question. Okay.
Sure.
But we will definitely go over that reason why we write positive base cases first.
So is it important that every problem have negative and positive base cases?
It is not important or necessary, but mostly there will be negative base cases also, because of the reason is that basically if you think about it, what you are doing is you are exploring all possibilities, right? All possible possibilities, that's what you are doing. Recursion is nothing but exploring all possible possibilities. So some of them will be good possibilities and some of them will be bad possibilities. So those bad possibilities are what correspond to your negative base cases, and good possibilities are what correspond to your positive base cases. Okay. About the order, it's not important. I mean, it's not, you can still code a recursive solution by writing the cases in any order that you want, as long as you maintain as long as you are correct about the base cases. So it's not strictly necessary to have positive first, negative later, but I will show you cases when we can potentially run into problems if we do it the other way. Like, you will have to take care of the case. If you are planning to write a negative base case first and a positive later on, then just make sure that that negative cases that you are writing is complete in itself. We will see what that means. But if you write the cases completely and you don't miss anything, then you can write them in any order. That should not be a problem. For convenience, we write positive first and negative later, because so the reason is, see, here, if you see, if you see here, when we take sum as 0, let's say you plan to write this first. Okay. So you would simply say that if you have reached the end of the array, if you just like by mistake, if you just say that if I reach the end of the array, I can return -1 or whatever empty array, then this is, and if you're writing this at the beginning, then this is definitely wrong. Why? Because there are two cases here. If you reach the end of the array and the sum is 0, then it's still a positive base case, right? So to avoid that, what we are saying is just take care when sum is 0, irrespective of what the I is, I know it's a positive base case. So I will write it first and then I can take care of the end of the array part. Like, do you get an idea what I'm trying to say? Asray?
Yeah, I get it. Yeah.
Yeah. If you straight away write if I equals to n return -1, that's wrong, right? Because there are two cases here. The sum can be 0, sum can be anything else. If the sum is anything else, then yes, it's a -1. But if sum is 0, then it's a positive base case. So you will have to then take that into account if you are switching the orders. You will have to write if I is n and sum is not equals to 0. Then you return -1. And then you can write if the other cases. Similarly, right? So that's basically one of the reasons. Otherwise, if you would have written if sum is 0 in the beginning, then basically you can straight away write if I is n, because if you reached here, basically sum is not 0. I mean, you have taken care of all the best positive cases. Right? Everyone else is fine so far? Do you understand any questions in the recurrence or in the decision making? So I showed you two types of decisions. We talked about include exclude, wherein we say that you can choose to include an element or exclude it. And the second, we talked about the case that you think about the first element of any subset. And we said that another view of this same problem could be that you divide it into n buckets, n categories, wherein in the first category, the minimum element is the first element. Similarly, the second category is the minimum element is the second element, and so on. So this is also one possible decision that you could have made. We will come back to this decision. Let me show you the code for this. Okay. And then we will make more changes in the code. So let's quickly code this. This is the login, right? DSP patches, DSP patches 1. So let's see. First things first, I will define my function. So what is my function? My function is f, which returns all possible subsets. So what is the return type of my function? It's a vector of vectors. Correct? Then the name, I can write any name. Let's write combination some helper. What are the arguments? The first set of arguments will be for the suffix array. So this is, let's say this is the suffix array. And then there will be for a sum, there will be an argument. So this is the prototype that I came up with. So you should be able to think about this prototype on your own without me or without you like breaking your head over it. This is the parameters in this particular in the function are nothing but they come from your recurrence relation or the sub problem, the representation of the sub problem. And the return type simply comes from the problem itself. Like your mission statement is telling you that you have to return set of all subsets. So that's what we have done, a set of all subsets. Any recursive formulation, we will have two types. We will have the recurrence and we will have the base cases. So I always write the recursive step first. So let's see. The recursive step is, let's exclude candidate start. Then I will get a set of all subsets. Correct? Let's say I get, so my sub problem is nothing but candidates start plus 1 and the same sum. So I get all the subsets without the start. This is 1. Let's say this is temp 1. The next case is I include candidate start. So in that case, let me get all possible subsets. So my sub problem is nothing but candidate start and target minus candidates start. Now what I will do, I will append candidate start to each of the subsets. So how do I do it? I could simply go over all the subsets of temp2. So each of these temp2i is a vector. What will I do now? I can do a temp2i dot pushback candidates start. This is how I have gotten this. Now my result is nothing but union of these two. Result is union of temp1 and temp2. So how do I take a union of temp1 and temp2? Let's say this is my result. I can first go over all the elements of temp1. I can push each of the vectors of temp1. Then I can go over all the elements of temp2. And I can push all, and I can return this result. This is the answer that I have to return. So this is the recursive step. Let's talk about the base cases. So let's write the positive base case first, that if you reach the end, then you can simply return a 2D vector where with just one set. So this is the positive base case. Let's talk about the negative base case. So one possible negative base case is that if your sum has become negative. So if either your sum becomes negative or you reach the end. So start becomes equals to candidates.size. In both the cases, you can return an empty array. And that should be enough. So here we will have a result, and we will say result is combination sum helper candidates, start is 0 and target is target, and then I can return result. Let's see. Okay, any questions in this implementation? I will just take a pause and answer any questions in this particular implementation. This is exactly that whatever we did yesterday. Yesterday also we wrote a pseudocode, similar pseudocode.
Sir, does the candidates is the whole array or the suffix array?
Candidates is the entire array, right?
Yes.
Suffix array I am denoting by the candidates and the start index. Right?
Yes, sir.
Anything else? So this implementation is clear to everyone? Can I have some acknowledgements? Okay.
Yes, sir.
Let's go to the second type of decision that we were talking about, and let's see how this can be done using that decision. So here in the second type of decision, we said that you look at the eventual answer and you see that it can be categorized into n buckets. This is your array. First you sort the array. That's okay. Just sort it. Now you say that there is a one bucket of elements which basically contain this particular number as the first number or the minimum in all the subsets. So we said that this is basically, if this was 2, we said that this contains 2 as the minimum, and then you can have numbers which are greater than 2 in each of the subsets of this particular set. And then we said another set of subsets will have 3. Let's say this was 3 as the minimum. Then another set will have 4 as the minimum if this was 4, and so on. So in these cases, basically, what will be your sub problem? If you make this decision that a particular ith element is the minimum in all the subsets corresponding to that bucket, then what does your sub problem boil down to? Your sub problem boils down to sum minus ai. You have to find this sum now in I to n minus 1, including I again. This part of the array you have to find now sum minus 3. Similarly, if you have 4 as the minimum, then in this part of the array you will have to find sum minus 4. So our recurrence relation for this case then becomes, again the parameters of this will be the same as the previous because these are the things that are varying. You see the sub problem basically boils down to a sum variable and a prefix and a suffix array. So you have f, ai and sum, and this is nothing but union over all from 0 to n. Over all j's, it will be basically aj union f of aj sum minus age. Correct? This is the recurrence we said. This part is any questions in this decision? Everyone is clear with this decision? So let's code it if this is clear to everyone quickly. So let's remove all this. So what will be my function prototype? My function prototype will again remain the same. I have to return a vector of vectors. And let's call it combination sum helper. What will be in the argument? A suffix array. So the suffix array can be represented by the array and a start index. And I will have the target sum that I have to make. We will come back to the base cases, but what is the recursive step? The recursive step is that all the elements from start to n minus 1 could be the minimum. So I will recurse over all these elements. Now the case is that I have to find all subsets with AI as the minimum element. So let's find that. Let's say that result is nothing but again a vector of vectors. And I say that temp is nothing but combination sum helper from I for some target minus candidates I. Correct? So I will get a subset and I can start populating my result also here by taking a union. Let me do that as well. So what I can do is I can start from 0, go over all the elements of this subset, and what will I do? I will say I will push back the current element, which is nothing but AI or candidates I. Candidates I, right? Yeah. And I can push this to the result. Then I can return the result. This recursive step is clear to everyone, what I wrote here? Do you follow what I have done here? Any questions in this recursive step?
Sir, please repeat the second for loop.
ये वाला loop?
Yes.
इस वाले loop में what we are doing is, yeah, this will be a temp j. Correct. Not temp I, sorry, temp j. So what we are doing is, see, this call will give us all subsets which with candidates I as the minimum. Correct? So you have to append candidates I to each of these particular subset, which is what we are doing in this array, and then I'm just populating my result with that. So what we are doing is we are iterating over every subset that we got with sum minus ci for the suffix array starting from I. Now what I do is I iterate over each of these subsets. I push the current element in each of the subsets, and I push the entire vector in my result also. Do you see what I did here?
Got it, sir.
How many of you did not understand this? Anyone? So then the base cases are again the same. If you reach the end, this will be your answer. This is now let's talk about the negative cases. Negative cases is if the sum has become 0 negative, or your start has become equal to candidates dot size, then you can just return an empty vector. Here what will you do? You will first sort the array. So let's sort it. So here we sort it and then we populate the result. Okay, so I'll just take a pause and you can ask me questions if you don't understand any part of this code with this particular decision. And if you understand, you can just acknowledge on the chat or by unmuting.
Sir, can you just discuss the complexity in both these cases?
Yes, we will. That's in the agenda for today. We will talk about the complexity also.
I mean, the runtime for this is 40 millisecond, and for previous one it is 56 seconds.
No, don't look at the complexity of a program from this value. See, if I run this program again, it will give me a different millisecond. Like generally, it's because it is, see, it's giving you 44. This is not a right metric what you get in the lead code server, because the server typically has a load. So there might be many other people who must be submitting at the same time. So this runtime, don't judge your program's fastness, or don't compare two programs by the runtime that you get from this.
Okay,
Okay.
sir.
We will do, but that does not mean we will not do. We will do the order analysis, the running time of both the codes.
Okay.
That is in. This is nothing but, see, Savio, this is how do you write an array? You can write an array as this, right? 2, 3, 4, right? This is one syntax that C++ provide. So how do you write an empty array? This. Now, how do you write? So this is an empty array, and if I want to, I can write something like this also. This is a 2D array of two comprising of two 1D arrays, one of size 2 having 1, 2, and one of size 2 having 2, 3. This is also, I can write this also. Okay. So how do I declare an empty, just one array with empty? This is how I declare it. I can declare 2 with empty like this. Did you get it, Savio? Any more questions? Oh. Yes, Karan, I can do that. What about others? Everyone else understands this, or should I explain the recursive step?
Sir, there is just one doubt.
Mm-hmm.
Sir, like you are doing nested for loop here. Can't we do it two for loop separately?
You can do a 2 for loop separately, but you will have to store the result of every. then you will need to have a 3-dimensional vector, correct? Because you will have to store the result of each of these in 2D vectors, and then after this you can go over each of them, correct? So you will need to have a 3D array then.
You mean we have to store candidate I for each separately?
We have to store all the temps if you want to do it outside. Here we are reusing the same temp again.
Okay, got it, sir.
So if you, how do you store a vector of 2D vectors, a 3D vector, right? So I was also thinking of doing that when I was typing, but then I realized that it will become complicated.
Sir, actually,
Hmm?
if we will if we will write this code, then sir, we might forget this one.
What will you get?
I mean, I was saying just that if we just write the similar code, then we will I will definitely forget to write this nested for loop.
Okay, okay. No, Rahul, you cannot just return. This will not work. I mean, do you see why it does not work? Because this function has a return type. If a function has a return type, then you will have to return something always. And the return type of this function is a 2D vector. So you cannot get away by not returning anything. You will have to return a 2D vector. So what we return in this case is an empty 2D vector. How is an empty 2D vector represented? Is just a, okay, Tulika? Yeah, we will come to that, Rahul. Don't worry. We will convert this into void only. Don't worry. Okay, people want me to explain the recursive step again. So think about the decision. What is the decision that we have made here? We have told ourselves that this decision is clear to everyone. I have just implemented this decision. So in this decision, what I'm saying is that look at the eventual answer. In the eventual answer, you have n types of subsets. Subsets wherein element 0, let's say this was 2, is the first element. Subsets in which element 1, which is let's say 3, is the first element. By first I mean the minimum. Similarly, subsets in which 4 is the minimum. And I have to take a union of all these subsets. Correct? So how do I find all subsets which begin with 2? So if I include 2 in my answer, then what am I left with? I am left with sum minus 2. Correct? And what portion of the array am I left with? I am left with the entire array again, because every element can be used more than once. If there was a constraint that you can use an element only once or at most once, then your array would have become this array. So what I tell myself is that if I want to find all subsets that begin with 2, I will find all subsets with sum minus 2 in this entire array. And for every such subset, what I will do is I will append 2. So this entire half, this half is I am getting from by finding sum minus 2 in this entire array, not in this half. So sum minus 2, when I'm getting sum minus 2, I can again get a 2. And then I am saying that this sum minus 2, so I have accounted for a 2 right here. So that 2 I have to account for when I am creating my subset. So I push 2. If this is not clear, then we can take an example that might help make things clear. Let's take this example wherein you have 2, 3, 4. and you want to make a sum of 6. So 3 cases. You can have 2 as the minimum, 3 as the minimum, 4 as the minimum. If you have 2 as the minimum, you are left with the entire array. That's what we are doing. We're doing a dry run only. You are left with the entire array and a sum of 4. If you take 3 as the minimum, you are left with this array and sum as 3, remaining sum. And if you have 4 as the minimum, then you are left with this array with sum as 2, remaining sum as 2. Correct? So what I have done in the for loop is I have iterated over all the elements of this, which is the first line of the loop. Then what I tell is get all the subsets from this branch. Whatever subsets I get from this branch, I store it in temp, and then I iterate over each of these subsets that I have gotten from temp, and I account for this too. So every subset I push to. Now this is the result from this half of the array entire. So what do? In my result, I put all of them one by one. Then I increment my I. I find all subsets from this branch. So let's say this was all subsets that from this branch. Then I account for this 3 by pushing 3. And then I put all of them in the result. So don't have to think about, just think about the decision. If we have 2 as the minimum, then you have to find 4 from this entire array. If you have 3 as the minimum, then you have to find 3 from the entire array, from this array. And so how do you find? You find 3 from this entire array. And what you do is for all the subsets that you get as part of that process, you append a 3 again, because this part of the subset sums to 3, but you want a total sum of 6, and you have already made up your mind that the first element is a 3. So you push a 3. So let's see a dry run. Then Sai, maybe you yourself will answer why this needs to be sorted. So if you have 2, if you take 2 as the minimum, you are left with 2, 3, 4 and sum of 4. Here again, you have 3 choices. You can have 2 as the minimum, 3 as the minimum, 4 as the minimum. If you have 2 as the minimum, you will be left with 2, 3, 4 again and a remaining sum of 2. If you take 3 as the minimum, you will be left with 3, 4 and sum as 1. If you take 4 as the minimum, you will be left with 4 and sum as 0. So this is a positive base case. So you will return empty from here. Now you return empty 2D array from here, and a 2D array with an empty 1D array. Now what you do here, you go over this. So when you go over this, you have one element in this, which is this. And what you do is you put 4 in it. Okay. And then so now from here you have one answer, which you have gotten from this branch. Let's talk about this branch. You have 1 remaining. You have 2 choices. You can make 3 or 4. If you take 3 as the minimum, you will be left with 3, 4 and a sum of -2. If you take 4 as the minimum, you will be left with 4 and -3. So both of them are negative cases. So what you do is you return an empty 2D array. Now, once you return an empty 2D array here, it will go over all the elements of this array, but this dot size is 0. So that loop will be skipped. So it will not do anything. Similarly, when this returns, the size of this is 0. This is temp. So temp dot size is 0 here. Here temp dot size, for this case, temp dot size is 1. So now it will return. It will not do anything again. This one also. So here you have basically gotten an empty, which you will return here. And here also you want to push 3, but you don't have any result from this half. So you don't have anything from this entire branch. And then finally, you will have this branch wherein you can take 2, 3 or 4. If you take 2, you will be left with 2, 3, 4 and a sum of 0. This is a positive case. So what you do is you return a 2D array with one empty way here. And what it does is it goes over all of them. So it just has one element which it traverses and it appends 2 to it. Correct? And then it will again return this here. So it will go over this, and it will append another 2. And it will return it here. It will go over this and append another 2. So here you will get a 2, 2, 2. So now your result, let's talk about this particular step. Here you will have, so let's talk about this particular case. Here you have a 2, 2 and you have a 4. From this branch you did not get anything. So your result that you return from this half is a 4, and from here you return a 2, 2. And in the result, you will push both of them. So this will be the result at this half, which you will return here, and here you will again traverse over each of them and put a 2. So you will put a 2 here, put a 2 here. So from this entire half, you got 2 results, 2, 2, 2 and 2, 4.
So can you repeat that 4 thing again? That 4 wala branch?
Ye wala?
The one in which in the end you have like 1 4 remaining and the sum is 0.
This one, right? 1 4 remaining and the sum is 0.
Yeah.
So this is a positive case. So you will return this. What is this? This is a 2D vector. This is of this type. This is a 2D vector with one element, which is empty. So when you are here now, what are you doing? Once you return from this branch here, you are in your loop. Correct? So this is temp now. What you do from this temp is this is happening inside the loop. You get a temp equals whatever f you have. This temp this will be returned from this. What you do now is you will go over all the elements of this temp. So when you go over all these elements of the temp, you have just one. So temp dot size is 1. So it will iterate once. You will enter this loop. So this will be the first element. Temp of I will be this. What you do is temp of I dot push back 4. So 4 will be pushed here. And you put this thing in the result also. The result is a global result for all the 3 branches. Here you have a result. That's how we have formulated this recursively, Devanshi, right? If there was not, if we did not need to include it multiple times, what you would have done is your subproblem would have reduced to sum minus 2 from this half of the array. But we said that we want a sum minus 2 from this half of the array. Similarly, when we considered 3, we said that we want a sum of sum minus 3 from this half of the array. If we had to consider it only once, then we would have said that we want sum minus 3 from this half of the array.
So at all points, the subsets, like the vectors that are part of the main resultant vector, they're only getting populated by that like append array ka wo start element. Only that step, right? Basically that for loop.
Come again?
Like the step in which we put in that, like the element in question, like say 2, in that 2 wala branch it's 2 or like 3, like that. So at any step, that is the only step that is actually populating the arrays, the vectors.
All the branches are populating the vectors. This will give you a vector of vectors. This will give you a vector of vectors. This will give you a vector of vectors.
Yeah,
Each of the vector.
But for every function call, it's only that for loop in which you append that like you push back that one element to all the subsets that you have, only that step is actually populating it, right? For every branch and sub branch.
Yes, in this example,
Okay.
you are talking about the inner for loop, right?
Yeah.
We had a
The
nested
one,
loop there. So the
uh,
outer loop was for these
yeah.
branches. And the inner loop was that once you get all the results from this branch, for each of those results that you get, you have to append a 2.
That inner for loop.
That for loop, yes, that is basically what is populating the result.
Okay.
Is there a way to know how many times the function will call itself recursively without doing the dry run? We will see. We will put an upper bound on that, Mrigank, very soon. Why does it need to be sorted? Sai, do you understand now? If your array was not sorted, let's say you had 4, 2, 3, then when you are saying that, let's say 3 is the minimum, then you are saying that in all the results 3 will be the minimum. Then basically if you say that 3 is the minimum in all the results, then what is your sub problem? Then your sub problem has to be 3 comma 4, right? In this array you have to find the remaining. But how do you represent this sub problem? This is a subsequence, correct? So you will not be able to represent it like so smoothly. If we sort it, then we will always have a suffix array as the sub problem, because if we take any minimum, we know that to the left of it or everything is less than this. So I don't need to consider them when I am populating for my sub problem. Did you get this, Sai? I will show you the code again. I understand it's not very easy to like grasp it in the first go. So take a look at it, and I can take a pause another minute or so. You can be sure, convince yourself that this works. And not only this works, you should be, so that's what I'm trying to say in all the lectures. You should be able to write. See, I never wrote this code imagining how the tree will unfold. I had no idea. I just told the decision and I adhered to the decision. I had a decision, I had a recurrence, I just stuck by it. That's it. I did not do anything else. I did not have any other picture in my mind when I was coding this. Just the recurrence, I implemented the recurrence, nothing else. So that's the whole point of the recursion lectures that I'm trying to like, you should have this, like inculcate this skill in you, that when you are writing this recursive step, the picture of a tree and unfolding should not be in your head. Otherwise things will become very messy. When you are writing it, it should just be from level 1. From the decision and the recurrence, you are just implementing the recurrence. If the recurrence is correct, everything else will take care of itself. Do you see what I'm trying to say here? So take a look. Let me know when we can move on.
But I still understand how you arrive at the decision and like what was the thought process behind making that decision.
You did not understand that.
Yeah, like how do you arrive at a decision in the first place? Like, and how
Yeah,
do
I
how
mean,
do you
that
know
will
that?
come with practice. I can, like, from the lectures that we will do, I will tell you the most important types of decisions that typically occur in every problem. Like a couple of them I've already discussed. Mostly these, and then maybe 2 or 3 more decisions are sufficient for solving most of the problems. But yes,
So
if you just get a problem like at in the first sort, it's very difficult to come up with these decisions and these recurrences. Okay, Shashank. Like it's not. I
yeah.
understand. It's not easy at all to think about this on your own. In previous way, we had two decisions: target minus. Okay, so what is the question?
So yeah, this is the doubt even I had yesterday. Like, we're taking only one case here, right? Why are we not taking both cases, like including the target and excluding the target?
No, why are we? See, every subset will begin with something, right? I am just taking that into account. I am enumerating over all the cases. All subsets will begin with some number. I am saying that that number could be 2, could be 3, could be 4. So what if it is 2? If it is 2, then this is what it is. If it is 3, then this is what it is.
Okay, because like even if we don't include the element, that will get included in some other bucket. That's what we're telling, right? Like let's say 2, 3, 4, 5, 6, and uh, we're taking let's say we don't exclude 2 here. So here we're including 2, right? Every time.
Yes,
Like
and everywhere else 2 is excluded, right? When you are
yeah.
populating a subset beginning with 3, you have excluded 2. When you are populating a subset beginning with 4, you have excluded 2 and 3 both.
Okay. Fine.
So just think about the decision as a whole, like just the independent decision. What was the decision? That the eventual solution will either have 2 as the first element, 3 as the first element, 4 as the first element. That's it. That's all the cases. There is no other case other than that. So I'm just iterating or recursing over all the cases. Similarly, in the previous decision, I was just saying that there is all the solutions will either have 2 or not have 2. So I will populate all the subsets without 2, and I will populate all the subsets with 2. It's just a decision. Like think about it independently. Don't try to unfold it. If you're trying to unfold it, might become like. Any more questions? We will just start building on this. So make sure that you understand this.
Sir, what happened when the when we get answer subsets in the answer?
When we get.
Sir, actually, I'm saying that if actually the order matters in the subset, then what we should do then?
Order will not matter in a subset, then you will have a permutation that you have to give. Subsets are order will not matter, but if I mean, you will have to tell me the question then.
I'm just saying that if actually if we take order into the count, like all the elements in the subset, they are arranged in the descending order. So then what else we take count?
One way is you could just sort the result one after the other. Here you can just sort before pushing. One very simple way is you just sort here. If you really want the results to be in order, if that is the question, you can do this here. That will ensure that it's sorted. The other way is that you enumerate in a sorted fashion. So if you are trying to enumerate in a sorted fashion, then you cannot push at the end. Correct? You will have to append to the beginning. So you can do that also. Do you get what I said, Akash? Here, yes. Instead of pushing at the back, you could push in the front. That will involve a rearrangement, which will not be order 1. Or the other way you could do it, you could say that this is the maximum. Like the decision could be around maximum, saying that 2 is the maximum in the result. So if 2 is the maximum, then you will recurse over every element of the array less than 2. So it will be a prefix sub array then. and then you can push 2 at the end. Correct?
Yes, sir.
That is also one way you could do it. Clear to everyone? Can I have acknowledgements, or if you are still confused, can you let me know that it's not clear? Okay. So if this is clear, then let's stare at the solution, the previous solution. Let's come to the previous solution. So let's see this solution. In this solution, no, it will not be considered Rashmi, right? Because I am enumerating in a specific order. So when I am talking about all subsets beginning with 7, that's why I said 7 is the minimum. So 7,1 will never be a case. It will only be 1,7. That's why I said that is the minimum. This code you are talking about? Include, exclude? In the include exclude array, first of all, array does not have duplicates. In your example, you have 1271. Array does not have any duplicates. It's given in the question. If array has duplicates, then yes, this will not give you the correct answer. We will come to that question also. That's there. Okay. Now look at this solution. What have we done? If you just take a step back and look at this, we have basically, for our sub problem, we have obtained an answer. We have obtained an answer for a sub problem, and for this particular problem, I am constructing the solution here. Correct? So here what I am doing is, I am constructing a solution to the original problem when I am talking about the problem itself. Another way this could be done is, you could construct the solution to the original problem in the base case itself. So what I mean by that is, just to understand that, let's do a very simple question. Let's say I have an array, or let's do even a simpler one. Let's say you have to find the product of A n times. Let's say this is the question. What is the question? The question is telling you to multiply 3 5 times and give you the answer. So basically it is telling you to multiply 3 5 times. Okay. Let's say this is the question. So for this particular question, one second. Okay. So for this particular question, how would we go about writing a recurrence? We would first say, let's talk about the representation of the problem. The problem can be represented by 2 integers, a and n, where a is the base that you have to multiply n times. Let's talk about the decision. The decision is that I can multiply A once. So this is the decision that I am making. What does that mean? That means that I can get the result of multiplying A n minus 1 times, and whatever I get, I can multiply A to that to be the result. Correct? So here our decision is nothing but we are saying that multiply A once. That's the decision that we are making, and we are saying that, okay, if I multiply A once, then what is the problem that I am left with? The problem that I am left with is I have to multiply A n minus 1 times. Correct? So from here I tell myself that my sub problem is nothing but A n minus I or n minus 1, correct, for this case. And the parameters will basically be the parameters of the sub problem. So I will have an A and I will have how many times I have to multiply these two parameters. Both can be represented with integers. So I don't have any problem with that. And I will write the mission statement FAI is nothing but I have to multiply A I times. And I will write the recurrence as FAI is nothing but I multiply A once, this is the decision, and I multiply A I minus 1 times. And the base case is, if you see what is changing, only I is changing. So what is the smallest problem? The smallest problem is that you multiply I 0 times, or let's say I 1 time. If you multiply I 1 time, what is the result? It's A. So this is the base case. So let's quickly write the function for this. So how will the function look like? It will return an integer, which is the product. You will have A and you will have N, which you want to multiply how many times. Your recursive step will be, you have to restore the product of A multiplied N minus 1 times and say that your result is nothing but A into 10. And you can return result. So this is your base, this is your recursive step. And what is your base case? Your base case is when N becomes 1. You know what is the answer when N becomes 1? The question is multiply A 1 time. So what is the product of A multiplying 1 time? You have 1. You have A. So you will return A. This is basically the recursive formulation for multiplying A n times. Correct? Till now, everyone is clear with this, the decision that I made and the subsequent sub problem that I was left with, the recurrence, the representation of the sub problem. Everything is fine so far? Now you stare at this. What am I doing here? Here, what I am doing is, I am telling myself that first I have, in order to solve a problem, what I am telling myself is, what you do is you solve the sub problem and then you combine that solution to obtain the solution to the original problem. That is what I have done. I have solved a sub problem first, then I have combined the solution of the sub problem with something to obtain a solution for the actual problem, which I have returned. This is one way I have done it. The other way I could have done this is, I could have told that, okay, you want to solve a problem. What you do is pass down your contribution to the sub problem. And combine the results in the base case. So what I mean by this is, it will become clear to you. So what I mean by this is, another possible way you could have implemented this was by having an additional argument, let's say int current product, which is cprod, which you initialize to 1 when you are calling this function from main. And what you do in the recursive step is, in the recursive step, you say that you first pass down your contribution. So what is your contribution at this step? A, correct? So what you do is you pass down your contribution by multiplying whatever you have gotten so far with A, and then you call, so you will say return F A N C prod. And in the base case, what you do is you use that result. So let me make it even more clearer. So what I'm telling you is pass down the contribution of this step through a, so I have introduced, what have I done? I have introduced another parameter which will keep track of each recursive step's contribution to the actual answer. Okay. So what I'm saying is pass down my contribution. What is my contribution? My contribution is A. So pass down my contribution to this C prod. So call this AN minus 1 C prod. And this is, and in the base case, what you do is, let's say in the base case, what you do is once you reach the base case, you will have the answer here, because every step, what you have done is you have started from the top, the biggest problem. Every step you are passing down your contribution, and in the base step, what you can do is base step, you will have the result in this argument. So you can just return this result. And then what happens is this result is returned here, which subsequently is returned here, which subsequently is returned here. And finally, this returns to the caller. So this is another way of writing the same code. Does this make sense, what I told you? Here, what we were doing was we were not passing down the contribution of each step. What we were doing was we were saying that get the result from the sub problem or from the smaller problem, and then I will use my contribution to compute the result to the actual problem and return them. So I get the result of the smaller problem, I use my contribution, and then I return the result. Another way of doing this is that I don't get the result of the sub problem. I just pass down my contribution. I introduce another variable and I say that this variable just keeps a track of the contributions from each of the steps. And I tell myself that pass down the contribution, my steps contribution to this, so that when you reach the base case, this particular variable will have the answer, because every step has passed down their contribution. And then you can return that result. This result has the answer. So this result basically will then get passed here. So let's do a dry run. Things will become clearer. Then we can abstract this idea. So what are we doing? Let's say we want to multiply. Let's say we want to multiply 2 3 times. So what are we doing? We are saying we have a C prod which is 1 to start with. Correct? So what we are doing here is we are saying that you multiply 2 times, and C prod is 1 into 2 now. Okay. Then what we are saying is now multiply 2 one time, C prod is 1 into 2 into 2. Then finally we say multiply 2 0 times and C prod is 1 into 2 into 2 into 2. Now this is the base case. So if you see in the base case, what we were doing was we were returning this. So this gets returned here, and here we are not doing anything after the call. After we called F, we were simply returning F. So this gets returned here and this gets returned here. So 8, 8, 8 gets returned and this returns to the original caller, the answer 8. Whereas in the previous case, what we were doing was, if we have to multiply 2 3 times, what we were doing was we were saying that multiply 2 2 times, multiply 2 1 time, multiply 2 0 time. So multiply 2 0 time is nothing but 1. Now here basically once we come here, we were contributing, adding the contribution of this step, which was 2 to whatever I have gotten from the below branch. So I have gotten 1 from the below branch. I was multiplying 1, 2 with it. The result was 2. I used to return 2 here. And then I here at this step also, once I have gotten this answer, I used to add in my contribution, which was another 2 and return. And here once again, whatever I have gotten, I used to add in my contribution and return to the actual column. This was what we have been doing. And this is what another way of doing the same thing. Do you understand this? So this, everyone? So this basically, this particular, this is another way of implementing a recursive solution wherein you don't wait for the result from the bottom, you pass your contribution, and then finally in the base case, you have the answer which you push. So if you have to go ahead with that, then let's see how we can modify this solution to take that into account. This was the solution to the problem. Let's come back to the solution. So let's see. So we will use the same decision as include exclude, and we will try to see how we can pass down the contribution. So if we exclude an element, what is the contribution that you are passing? Nothing, correct? If you include an element, what is the contribution that you are passing? Candidates of I. So what I can do is, I will have the same return type. What are the parameters? Three parameters I had from the recursion, which was first the suffix array. So this is the suffix array, and the sum, which was this. And finally we have here, now I will have one more argument, which is nothing but the contribution, which will store the contribution of every step. So let's say this is current set. Okay, just see how this works. I am at the recursive step. First case is I choose to exclude this element. So if I exclude this element, I will What is my contribution at this step? Nothing. So what I do is I will call the same function. If I exclude it, my will be start plus 1 with the same target, and I will not change my current set. Okay. If I include this element, my contribution at this step is candidate start, correct? So what I do is I can create another temporary array, which is, let's say, current set temp, which is nothing but let's say this is it. And what I will do is now I will include my contribution in this current set temp, which is nothing but candidate start, and now I can call this. Passing down this contribution. This is current set temp. This is the contribution that I have passed. And finally, I will take a union of both. So this is fairly easy. Let's say I have to take a union. I can go over all the elements of first temp. I can push the results. I can go over the results again of temp2, and I can push the results again, and I can finally return this result. So this is the recursive step. Let's talk about the base case. I will have the positive base case. So in the positive base case, what was my positive base case? That if my target, if I include it, this becomes sum, right? Start. If target becomes 0, then what will I do? I will return the current set. This is the contribution that I have accumulated from the root to the leaf, and I am just passing that result. Negative base cases are fine. That if target is negative or start is, then I can continue to return an empty one. So this is another way you could solve the same problem. So in this case, then what you will have to do is you obviously have a result vector. You have a current set, and you can call combination sum helper with candidate 0, target, and current set, and I can return result. So what do I have to do? Here I will have to pass it in the form of a 2D vector. This is giving your memory limit exceeded because
Sir, I guess we did not decrease the target.
we did not decrease the target. You are right. When we contribute, right? Right? This is the only thing. No, exclude
As
में
for
नहीं
no
आएगा ना वो.
contribution, sir.
Correct. Now see the solution. What I have done. I have just implemented the idea that I told you, wherein I passed down the contribution. Is it making some sense to you guys? At least a little bit. If not, I understand it's difficult to understand everything in one go. But are you getting some intuition as to what we are doing here?
Could you explain once again what the curve set is having exactly?
Yeah, we will do a dry run. Let's do a dry run and things will become clearer. We will discuss the complexities outside. Let me just complete the entire recursion template at least. So let's make this idea even more concrete, a little more concrete um, through an example. Let's take the same example that we have been doing all this while, 2, 3, 4, and I want a sum of 6. So to start with, my current set is an empty. It's a 1D array which is empty. And my sum that I need to find is 6. So these are the arguments. Now I have two cases here. I can choose to include 2 or exclude 2. So if I include 2, then what I am left with is 2, 3, 4. In the current set, what have I done? I have pushed back 2. So my current set now contains 2. And the sum that I have to find is 4. If I exclude 2, then what I am left with is 3, 4. And the sum of current set is still empty and the sum is 6 that I have to find. Now let's go down further. I can choose to include it or not include it. So if I include 2 again, I will push 2 again in the current set, which is what I have been doing. My sum comes down to 2 and I am left with 2, 3, 4. If I exclude it, then my current set has 2. My sum is still 4 and my array that I have left with is 3, 4. Let's take a decision here. If I include 2, Then I will push 2 in the current set, which is 2, 2, 2. My sum becomes 0, and I am left with the array 2, 3, 4. Let's come down here. If I don't include 2, then I am left with current set as 2, 2, a sum of 2 with in the array 3, 4. Now see, this is a base case. So in the base case, what we are doing is now we are returning this because we have propagated this all the way, this 2, and this 2. And we have constructed the answer here. So we will return this 2, 2, 2 to the parent. Previously, what we were doing was we were not propagating this. From here, we were returning an empty subset. And this guy was putting a 2, this guy was putting another 2, and this guy was putting its own share of 2. And then the eventual answer of 2, 2, 2 was getting constructed. Here we are constructing it as we go down. And then finally we are propagating the final result up. Let's come here. You can choose to include 3 or not include 3. If you include 3, you will have a 2, 2, 3 sum of -1 in 3, 4. This is a negative case. So from here you return an empty 1, 2D array. So this is, you don't get anything. If you don't include 3, then you are left with 2, 2, a sum of 2 in 4. Two cases again, you can include 4 or not include it. If you include 4, you have 2, 2, 4 sum of -2 in an empty array. So this is again, you return an empty. You don't return this, you return empty if you see the negative cases. So this again, this branch does not have anything to contribute. Here you return, here you, if you don't include 2, you will be left with 2, 2 in the current set, the sum is 2 and an empty array. So in an empty array, this is again a negative case. So you basically don't return anything. You return an empty subarray, so you don't have any contribution from this branch. So this branch then in turn returns an empty, and this branch has written empty. So empty union empty is empty. This branch returns empty. This branch now has empty union this. So which is this? Now this keeps on returning. Visible now? Saurabh, visible now? Okay. So if you want to do more steps, let's consider this branch. You can choose to include 3 or exclude it. If you exclude it, you will be left with 2, sum 4 and this 4. Here you can choose to include 4 or not include it. Let's say you include 4. So then you will be left with, you will push 4. So you will have 2, 4 coming down here. Sum is 0 and you will have an array of 4. Now this is again a positive base case. So you will return this upwards. So 2, 4 will get propagated all the way. Here you will basically take a union of 2, 2, 2 and 2, 4. So here you will return 2 arrays, 2, 2, 2 and 2, 4, which gets returned here. Is this getting clear to some extent? What am I doing here? This is another way we could do things, wherein we pass down the contribution at every step and we construct the answer in the base step. The other way that we were doing previously was that we were getting the answer from the from the branch and then adding its contribution to arrive at the solution for the original problem. So this is another thing that we could do. Okay, this is clear to everyone. Shall I move ahead? Just one more thing. Okay, so far what we have done is, in the first step we looked at a template for solving recursive problems, and we said that in the template that we will be using, our arguments will typically be a representation of the subproblem that we want to construct. Then we said that we can do one more thing. We can pass down the contribution of each step, and in that case then I will have to modify the prototype of the function to have two types of arguments, one set of arguments which represent the subproblem, and then another set of arguments which represent the contribution. We will do one more thing, but before that, let's take a digression. Let's say you have a program wherein you want to add two numbers and return the result. What are the two types of function prototypes you could write for this? So I will tell you, the question is add two numbers and return the result. So what are the two types you could have a prototype? One prototype is you could say that explicitly I will return a sum, and you can have two arguments here. And in the body of the function, you can return a plus b. So that in main, when you are calling it, you will say that result is sum 2, 3 and return and see out. You can print result here. The other way you could define a prototype is you would say that I don't want the function to explicitly return anything. Instead, what I can do is I can take another argument by reference, so that, and I will change that argument in the body of the function. So what happens then in the main is you can simply call sum with 2, 3, and you, let's say you have an integer variable result and you pass this result, and then you can see out that result again. So what happens is, because this is passed as reference, so result, let's say this is the memory location for result. C will also point to this, or C will also be named by, C will also name the same memory location. And then when you are doing A plus B, the result will come here, which can be accessed by this function also. So we can have two ways of returning something from a function. We can have an explicit return type, or we could choose to not return anything explicitly from the function, but have an implicit return value by passing it by reference. Correct? So this pass by value and pass by reference is clear to everyone? Yeah, some of you might already be knowing it, but good to recap. So now I tell myself that let me look at the problem. The problem that now let's come back to the actual problem, the subsets problem or the combination sum problem. Now I'm telling myself that, hey, I have to return a vector of vectors. And every time I call this function and I assign it to temp, let's say, a new copy of this is getting created for temp in the memory, right? Every time. So I tell myself that, why do I want to do this? Instead, let my function not return anything explicitly, but have another argument in its signature, which is taking this result as reference. And this result basically is coming from the main itself. And what I will do is I will populate this result. So the summary is that if I have recursions wherein I have to return an array or a 2D array or something which takes up a huge amount of memory, I would not, or it's not a good idea to have an explicit return type for these functions. Of course, if you want to return a Boolean or an integer, it's okay. You can have an explicit return type for recursive functions. But if I want to return an array or a 2D array or something which, some data structure which takes up a lot of memory, explicit return type is not a wise idea. Instead, I will pass that as reference in as one of the arguments of the function. So the summary is that my function signature will have 3 types of arguments in all when I'm constructing a recursive solution. The first set of arguments, which are probably the most important arguments without which you wouldn't be able to solve a question, are the arguments corresponding to the subproblem representation. The second type of argument is basically nothing but your contribution that you want to pass. And the third type of argument is the return value that you want. And this will be passed as reference. Let's extend the same question to incorporate this third type of argument.
So we may or may not have the contribution, right? If you want to do recursion in the other method, where you just
you can choose to not have a contribution. Yes. So let's talk about the same question. I will have another argument here, which is nothing but a vector of vectors, which will be my result. Now, let's talk about the recursive step. I will not need this now because the return type is void, which I will make now. Here, I can simply pass down the result. Here as well, simply pass down the result. I don't need this again, and I don't need any of this. In the base case, what I will do is, if my target has become 0, I will push the current set with the contribution to this, and I will simply return. I don't have a return type first of all, so I will simply return. In the negative base case, I can simply return. And here I will pass this as an argument and return this result.
So why did you remove those 2 for loops for union?
First 2 for loops for union. Let's do a dry run. I will explain. Because there is only one copy of result, which is there, which is this result. So every append or every pushback that you make persists. Correct? This is not result 1 and result 2, right? This is the same result I am passing, which is basically this result. So once I have done executing this line, I would already have the results of this subproblem in this result.
Oh,
and what
okay,
I need to do is, then I'm just, when I'm calling this, everything like the remaining will be appended.
Okay.
We can do a dry run.
Yeah.
Yeah. First of all, is everyone like with me so far? Like, I'm not going too fast, right? I understand this might take some time to digest, but at least you are getting some idea, right? What I'm trying to say. Yeah. So let's do a dry run of this eventual answer, and we will see how it is, how things are evolving. or unfolding. So let's take the same cliched example wherein we want to have 2, 3, 4 and a sum of 6. So when you call this from main, you will pass an empty vector in the current set. These are the arguments, an empty vector and a result vector. This result vector is also an empty vector to start with. Okay. Two cases, you can choose to include 2 or not include 2. If you include 2, your subproblem becomes 2, 3, 4 with a sum of 4. In the current set you push 2, your result is still empty. Now again two cases, you can choose to include 2 or exclude 2. If you include 2, you will be left with 2, 3, 4, sum of 2. You will push 2 in the current set, your result is still empty. From here you have two choices, you can include 2 or exclude 2. If you are including 2, you have 2, 3, 4, sum 0, 2, 2, 2, result is still empty. This is a positive base case. So what you do now is you push this entire array in this result. So what happens now is, now after this step, your result is this. So now you are done. So you come back. When you come back here, this result is still this. Why? Because it was passed by reference and this memory location is from the main function. This memory location is not a local memory location of this particular function. Correct? That's why now when you come here, this result is not this and not empty. Whereas these and this sum and this array will still be this array and sum of 2, not sum of 0. Because these are local copies, whereas this is a reference. So the copy is still from the main memory. Then you can go back again. So this will persist always. Now, if you want, you can go through other branches. Here if you don't include 2, you will be left with 3, 4. Sum of 2, current set is 2, 2, and your result is now this. Now you have two choices here. You can choose to include 3 or not include 3. If you include 3, you will be left with 3, 4, sum of -1. You will push 2 to 3. Your result is still this. Now this is a negative case, so you don't do anything to this. You simply return. So you return here. So this result still remains intact. Are you
So
getting an
basically,
idea?
like in the base case, when you push the value to the result, like all the answers will be stored in the result in the main function, right? That's what it's saying.
Yeah, I mean the memory is of the main, right? For that variable,
Yeah.
for that
So,
2D array.
so when
Everything is
target
getting
equal to 0,
appended there. Come
yeah.
again?
So when target equal to 0, that's when you're pushing all the subsets into the
Yeah,
result,
every
right?
time you get a target of 0, you push the subset, the current subset.
Yeah.
Are you guys getting some idea? Everyone, can I have like, I have spoken a lot in the past half an hour. Can I have an appreciable number of acknowledgements for this? Okay, it's not becoming too much, right? All good so far? Yeah, so this is what we will be doing in all the questions. This is basically the the final answer. So let's do another exercise. Yes, you will need to pass the size of the array, the current size. You're right. Okay. So what time is it? It's 10, right? Let's do the same exercise. So try this then at your home. The same question, which is nothing but the combination sum question, which is this question, the combination sum question. Try it with the second decision, incorporating all these elements of recursion, like the contribution passing step, as well as the return, implicit return value, and the decision of being the first element being the minimum, second element being the minimum, third element being the minimum. Okay. So you will try that, or should we do it in the class? Yeah, just try that. Now that you have some idea, this credential is anyways available to you guys, so you can stare at the code for as long as you want after the class, and do some dry runs in your head, and things might become clearer to you. Yeah, I will code it for you tomorrow if things become a little too difficult to handle. Okay. If that is the case,
Sir, could you repeat the question again?
the question is the same question, combination sum. This is the question. Try this with the second decision. So the first decision, which was include, exclude, we tried all the three cases, right? The first case was wherein we did not have the contribution, we did not have the implicit return type. Then the second case was we had the contribution and we did not have the implicit return type. Then the third case, which I coded just now, was we had all the three elements. We had the implicit return type, we had the contribution, and we had the other arguments. So this was all with respect to one decision, which was the include, exclude. Now I'm telling you with respect to the other type of decision, which I told you, which was take this as the minimum, this as the minimum, this as the minimum. I have coded one solution for you wherein we did not have the implicit return type, we did not have the contribution. Try to code the other two parts wherein you pass down the contribution first, and then in the third step pass down the contribution as well as have an implicit return type, return value. Okay, for the second decision, second type of decision that we did. Yeah, try that. Meanwhile, we will do this question. So all of you had dinner, right? All good? Do you need a break? What about others? Okay, let's do one thing then. How much time do you need, Karan? Let's have a break of, yeah, my meeting, I just, I don't need a break right now because so I mailed my manager as well as I pinged them in the group. So some of them, like, because it's in the US time, some of them are still like not ready for the meeting. So it will still take some time before they are ready. It happens every time. It's always like the meeting is scheduled for 9 or 10 and it happens like around 12 or 1. Once they are ready in the afternoon, they have kids and they make sure that breakfast for their kids is done and then they start the meeting. So it is like that. I knew that somehow, so that's why I did not take a break. Like I was talking to them on WhatsApp and email as well. So I am fine, but if you guys need a break, we can have a break of maybe 15 minutes, because what about others? Can you put in your votes? You need a break or not? Okay, let's continue then. So look at this question that I told you. I'll just rephrase the question. Just let me know once you're done reading the question. Then we will see how to go about it. So this question is telling you that you have an array of numbers, all distinct numbers. You have to enumerate all possible permutations of this. So what are permutations? Permutations are nothing but arrangements. Correct? So first of all, tell me, for an array of size n, where all these numbers are distinct, how many such permutations are possible?
5 factorial.
N factorial? And how did you arrive at this? Yeah, I know there is an STD function next permutation, but we have to enumerate all possible permutations. So you will basically do that for n factorial times. Is that what you're saying, Mantavya? So how did you arrive at this n factorial? You say that there are n places that I have to fill. In the first place, I can fill any of these n numbers. So I have n choices. Second place, I have n minus 1 choices. Third place, I have n minus 2 and so on. Final place, I have 1. So the total number of possibilities is nothing but the product of this, which is nothing but n factorial. This is what is JEE maths, right? I was never good in maths, but still, if I know this, then you guys must also be knowing this. Yeah, quota diaries. So this is n factorial. Just a follow up. How many let's say you have this 1, 2, 2, 3, 4, 4, 5. For this, how many possible permutations? I mean, you should tell me. I am too old. I don't remember these things.
So 7 factorial by 2 factorial into 2 factorial.
7 factorial by 2 factorial into 2 factorial. Right? 2 factorial for this, 2 factorial for this, and a total of 7 numbers. So 7 factorial. Yeah, it took me a while to recollect this. Like I have become old now. Okay, so now what I have to do here is in this question, I have to enumerate all possible permutations of this array. So Let's do it recursively. First of all, the representation of this problem. Let's see the decision first. So what is the decision that I can make? Again, the decision is always hinged on the final answer. So in the final answer, I will have n factorial different permutations. So what can be the decision that I make? I can split this entire result into n possibilities, n sets, and I say that this set is basically all permutations that begin with 1. This set is basically all permutations that begin with 2. This set is all permutations that begin with 3, all permutations that begin with 4, and all permutations that begin with 5. Correct? And then my answer is nothing but the union of all these. So with this decision, what is the sub-problem that I am left with? So let's say I want to enumerate all sets with 1 as the beginning. This is first sub-problem that I have to solve. So how do I find all sets with 1 as the beginning? I can find all subsets for or permutations for this and append 1 to it. Correct? So I can do a 1 union all these permutations for array 2, 3, 4, 5. This is the first set. What is the second set? For when I fix 2, how can I get all permutations of this type? I can tell myself that get all the permutations of this array 1, 3, 5, 1, 3, 4, 5. Whatever you get, all the permutations, union 2 with it, or push 2 in the beginning. Correct? Similarly for others. So far clear? Others clear? So what is my sub problem then? So if I fix 2, I say that I want to enumerate all permutations with 2 as the beginning. What is the sub problem? The sub problem is 1, 3, 4, 5. Correct? So this and this, how are they related? Isn't this a subsequence of A? Do you know what subsequences are? So a subsequence of any array is nothing but you take some elements of this array in the same order, 0 or more elements of this array in the same order. So subsets, we did not have any order. So 1, 3, 5, 3, 5, 1, both of them are subsets for this array, but 3, 5, 1 is not a subsequence of this because the order has to be maintained. But 1, 3, 5 is a subsequence of this original array. Subsequences are basically you take some of the elements, not all the elements, 0 or more elements from this array, and that set is a subsequence of A. So now here if you see, isn't this a subsequence of this? Isn't this a subsequence of this? So far, is it clear? Like two things, the decision and the subproblem as a consequence of the decision. Ask me questions. I will take a pause. What about others? Where did you get confused? So these subsequences are clear, right? As subsequences as a subproblem, clear to everyone. So this was step one, the decision. Step two is basically the subproblem. So what is my subproblem? My subproblem is nothing but a subsequence. So from here, I come to step three, wherein I have to define the prototype of the function first and the mission statement after this. So tell me, how do you, if so far it's clear, tell me, how do you represent a subsequence mathematically? Like the suffix subarray, I told you, you can represent it by the array and a start index, correct? How can you represent a subsequence similarly?
The array and the visited element, right?
Yes. The array and another visited array. This is a Boolean array, which basically contains 1 for all the cells for which the elements have been selected, and 0 for the cells corresponding to which elements have not been selected. For instance, if you take this 2, 3, 4, 5, and let's say you are talking about a subsequence 3, 5, one of the ways you can represent this is you say 2, 3, 4, 5 and a Boolean array, which is basically of the same size. This will be 0, this will be 1, this will be 0, and this will be 1. Correct? You can represent it in this way. So then my function will have, what are the arguments? 3 types of arguments. The first set of arguments are for the subproblem. So what is my subproblem? My subproblem is just my subsequence. So I will have an array and a visited array. Okay. What is the second? This is the contribution. So what will be my contribution? It will be again a 1D array, because the solution eventually is a 1D array, like every contribution. And finally, my return, the third is the implicit return type, which will be a 2D array, which will be a vector of vectors. Correct? And what is the mission statement? The mission statement of this is it returns all permutations. It does not return, it populates all permutations in result of array A for comprising of all cells for which visited I is true. Right? And if this is the mission statement, then what we have done, what we are doing here is the recurrence, then the fourth step. The recurrence then becomes f a visited current set, and the result is nothing but union of what you do is you mark from j from 0 to n less than n. You mark visited of 0 to be true, visited of j to be true. Whatever you get from this subsequence, and then you take a union with aj. Right? This is basically what we will do. So far, all good? Can I have some acknowledgements? Because then I will straight away go to coding it. Are you able to like in your brains come up with this solution? So the idea always, whenever I teach, you should understand, yes, what I'm saying, but you should understand that how I arrived at it also, like what's going on in my brain when I am given this type of a problem. This is what is going on in my brain. I see that I make a decision, then I see, oh, because of the decision, the sub problem that I am left with is a subsequence. So then I immediately take a call. Okay, so if it is a subsequence, then I have to take a visited array and the original array. That's how I represent a subsequence. And then I say, okay, other two parameters are in place, which is the current contribution and the result. And then I write the recurrence with the recurrence from the decision that I used.
So I didn't understand the subsequence part. Like, first we split it by the starting element, and then after that the subsequence part I understand.
Which part you didn't get, Sasank?
So like, okay, let's take one batch, like starting with one. So what is the?
Let's
how are
do
we?
a dry run. Dry run always helps. Okay. So let's say you have 1, 2, 3. You want to print all permutations of this. To start with, you have 1, 2, 3. Your visited is 0, 0, 0. Your current set is empty. Your result is empty. You have 3 choices here. You can fix 1 as the first, 2 as the first, 3 as the first. If you fix 1 as the first, then your array becomes 1, 2, 3, 1, 0, 0. Current set, you push 1, which is the contribution, and result is still empty. If you take 2, then you have 1, 2, 3. Your visited array becomes 0, 1, 0. Your current set becomes 2, and your result is still empty. If you take 3, then your array is still 1, 2, 3. Your visited array is 0, 0, 1. Your current set is 3, and your result is empty. Now let's come here. Here you have 2 cases because only 2 zeros are there. You can either take 2 or 3 as the first. So let's say you take 2 as the first. So what happens if you take 2 as the first? You have 1, 2, 3. You will have 1, 1, 0. You will push 2, but your result is still empty. If you take 3 as the first, you will have 1, 2, 3, 1, 0, 1, 1, 3, and empty. Similarly, here also you can take 1 or 3 because these are only 0. 1 is 2 is already taken. So let's say you take 1 as the first. So in that case, it becomes 1, 1, 0. You push 1, it's empty. If you take 3, it becomes 0, 1, 1. You push 3 and the result is empty. Here you can take 1 or 2. So if you take 1, you are left with 1, 0, 1. You push 1, the result is empty. If you take 2, you are left with 0, 1, 1, right? Yes, 0, 1, 1. You push 2, so you have 3, 2, and your result is empty. This is the second level. Finally, now you have just one choice, 3. So you will push 3. And now you will have all ones. And here you will have pushed, yeah. So now your result is still empty. Similarly, here you can only push 2. So it will become all 1, 1, 1. 1, 3, 2 is the current set with empty result. So now this is the base case. When is the base case reached? The base case is reached when the visited has become all ones. So when the visited has become all ones, you know that you have taken every element into account. So then what you do is you push the contribution into the result. So now this result becomes 1, 2, 3. Here, now when you're doing it for this branch, this is the base case. By this time, the result will be 1, 2, 3. If you went there here and then from here you are going here, then your result would already have 1, 2, 3. Here you again reach a base case because all the visited becomes 1. So you will push 1, 2, 3 was already there. You will push 1, 3, 2, and you will go back. Now you will enumerate, expand this branch again. So you will have 2 here and then you will have 2 there. So you will have 6 permutations in all in the result. Do you see how this is unfolding with the current set and the result? Some of you? Yeah, so we will just code this basically. Let me just open the permutations question. So we will have, let's define the prototype of the function. It will be void because I know that this is not a primitive data type that I have to return. It's a big this is a huge big size, so I don't want to pass it explicitly. I will use an implicit method of returning. Permute helper might be the name of my function. The first set of arguments corresponding to the sub problem, which is the vector and a visited vector. Then the second set of arguments for the contribution. We can have another array. And finally, the third set of arguments, which is nothing but corresponding to the eventual result, so which is a 2D array. This has to be passed by reference always. Now let's talk about the base cases, or the recursive step. So in the recursive step, I can have any step only if it is not visited. I will visit it. I will push this contribution. Which is num psi. I will now call for the remaining. That's it. There is, I can return. What is the base case? The base case is when all ones. So I can write that also as if my current set size becomes equals to, has become equal to num size. Then also I have reached the base case. Then what I will do, I will just push back the result of the current set because this is the current contribution. And I can simply return. There is no other base case. And when I'm calling this, I can have a Boolean vector which will be of num size initialized to false. I will have a current set and I will have a result. Call permute helper with nums visited, current set and result, and result. There is okay. This is all that I have done, which is strictly in accordance with what I decided. There is just one thing that's missing here. Can you tell me? Yeah, sir, you are right. I want others to appreciate this. So when you are preparing for the next iteration, in that next iteration, the previous I, you don't have to keep it visited, right? That has to be reset to 0 so that in that branch, it can be considered again. Right? Do you see what I said here? I will have to make this false as well after this. And I will have to remove this element also. Does everyone, first of all, do you understand this code? Do you understand why I made this, the reason behind these lines? Others? Yeah, Drishan. So what I'm saying is just think about the decision that we made. What was the decision? The decision was that I will make that as visited because I'm considering that as the first element, and then I will call it on the other elements which for which it is still 0. So in the next iteration, when I'm about to consider another element as the first element, then for that particular iteration, my visited of the previous will also remain true, which is wrong, right? Because see this. If you see, if you go down this path, you have made this to be true. Now in the next iteration, you will go down this path, but this cannot remain true now. This has to be made false before you make this true. That's what we have done when after we come back from this branch, this entire branch. And the other thing is this set 1, 2, this is now 1, 2, but I want just 1 here. So how do I restore it? I pop this 2 from here. And then in the next iteration, I will push 3 in this. कुछ समझ आया क्या? What about others? So these are all coming from the decision itself. I'm not doing anything fancier than this. I just have a decision which I'm implementing. No, sir, your current set will not be passed by reference. Whatever it is, even if you pass by reference or by value, you will have to pop back, even if you pass it by value. Because once you return here, your current set cannot be 1, 2, right? For the next iteration. So before you entered this branch, what you did was you already pushed 1, 2. So even in this copy of the current set, you have 1, 2. That's why you have to return, even if you pass it by value. You will have to pop.
Sir, does the base case represents like the number of elements there in at the last branch?
Come again?
Like you said, the while writing base case, we wrote base case equal to the size of that array, right? That nums dot size.
Yes. So it is the same as saying that you have seen all the elements of nums. Visited is all 1 at this point. For every visited, every time we set a visited, we push in the current set, right?
Okay, so there we write like 1, 1, 1. So that's the size, right?
No, current set dot size is the number of elements in current set.
Okay, okay, sir. Last, okay.
Yeah.
Sir, in the base case, what were you returning here? And that is the empty vector which we are returning.
I'm not returning anything. The return type is void. I'm not returning anything. I'm just pushing the answer whenever I have, because I'm passing down the contribution at every step. Whenever I reach the base case, I would have an answer, which I will push to this.
So could you just go through again like how you arrived at the solution and all the steps like in one go? Just
yes. No, we don't pass anything. The pop back is always by default the last element. Yeah, I can do that. Can someone else do that for me? Then I will also do it. Pranav, can you do this? Like go over all the steps. What all did we do?
Okay, sir. Sir, the pop back steps, like the backtracking steps.
I mean all the steps at how I solved this question from the decision, the template.
Okay, sir. So could you put up the code, please? And
You want to see the code or the board?
code, sir. That's okay. Sir, so first of all, so we do like to mark which all positions we have visited. We keep a visited array and visited vector and the original vector. And like I'll start from this recursive call, whatever that is.
No, just start from the decision. Like, how do you solve this when you are given this question? Like,
Okay.
how do you from the decision itself?
Yeah. So our decision for a permutation would be which is the first element. Like जो भी हमारा string है वो कौन से element से start हो रहा है.
ठीक है.
So for that we maintain a visited array to mark which elements we have visited. So if our visited element, like the position of our visited, like if we haven't visited index I, first we mark that as true, then push it to our current set. We are basically building one permutation now.
Yeah.
So we push it to the current set, and after that, for the remaining of the positions in the vector, we call the function again. So it will give us the permutations over like inside this.
Yeah, I mean, that's basically what. So I'll just summarize what we did. So we have to take a decision at any point. So we said that our decision is nothing. If we look at the eventual answer, your answer will have n types of subsets. First category of subsets will all begin with 2. The second category of subsets will all begin with 3. The third category of subsets will all begin with 4, and so on. So I told myself this. The fourth category will all begin with 5, and so on. So now so this is the decision that I made. So now I'm looking at the sub problem. So what if I make this decision? So let's say I consider the case when I want to get all the subsets with all the permutations with 3 as the first element. So in that case, if I fix 3 as the first, how can I generate the rest? So I can generate the rest by finding all the permutations of 2, 4, 5. 2, 4, 5. All the permutations of this will go here, and then I can fix 3 here. So from here I arrived at what is the relationship between this and this. And I said, oh, these are subsequences. This was the problem, and this is the sub problem. So I told myself, oh, sub problem is nothing but a subsequence of the original problem. So if my problem can be represented as an array, how do I represent my sub problem, which is a subsequence? I tell myself that I can represent it as an array and a visited vector, basically which has a 1 here and 0, which has a 1 here and zeros everywhere else, so that to indicate that these elements have not yet been visited. So that was the first thing that the two things, the decision and the after the decision, we came up with the representation of the sub problem as well as the function prototype. So now our function prototype, as I said, will be this sub problem and a current set to pass down the contribution and the result. So from here, we then went on and we said that, okay, this is the prototype, and the mission statement is basically, it tells you to the mission. Then I write the mission statement before writing the recurrence relation. So the mission statement is that I want to populate all permutations of array into visited, basically of this array. The array for which the subsequence for which the visited corresponding visited is 0. So I want to populate all permutations of that in result. That's the mission statement. So that's the third thing that we did. And so decision, subproblem, mission statement. Now we went on with the recurrence, and we said that then our recurrence is nothing but union of all these. So this I can generate, and I can append a 4 to all of the sets. I can append a 5 to all the sets. I can append a 2 to all the sets, and I can take a union of all this to find the original answer. So that was basically the recurrence. So what is the base case then? The fifth step is the base case. So how do I get the base case? So if you see the base case, what is changing? Your subsequence is changing. So your base case is an empty subsequence. And how do you represent an empty subsequence? It is nothing but the entire array and ones in all of those indices for the visited, from the visited. So then this is basically the base case. Another way that you could do a base case is you say that because the contribution I am passing, once I have n contributions, then that is the base case, because that means that permutation is always of length n. So if I have n contributions, I know that is the base case. So that is also another way I could go ahead with the base case. And then the sixth step was implementing. So how do you implement? You have the base case. In the recursive step, you go over all these elements. You mark them as visited because subsequently you don't want them to be included. You are fixing them as the first. So you are getting, and then you get all the permutations by fixing that particular I. And then after that you prepare for the next iteration, and in that preparation you do the two unwinding things wherein you mark it as false and you remove the current element from the current set, so that in the next iteration you have the same visited array as it was when you entered. And so that is basically the summary. Does it help, Sasank?
Yeah.
So just always think about it in level 1, how you would come up with a solution. Don't go into implementation details too much. Just think about it from a level 1 perspective. What would you do if you are given this? You would make a decision, then you would define the subproblem, you would write the mission statement, define the recurrence, define a base case, and just implement that blindly after that. And then after that, you can do a sanity check wherein you are dry running this by drawing a recursion tree.
So, but like, why do we need that Boolean array? We can just slice the main vector based on only the like.
How do you
Then
how do you can slice it?
Slice. I don't know why they can do it in C++.
Yeah, I mean, you can do that. You will have to decide your arguments accordingly. Is all.
Yeah, like argument will just be the.
You can choose to not have a visited array and copy also. That also is fine.
All we need to extract is the 245 sequence and again pass that to the main recursive function. That's all that's happening, right?
Yes.
Yeah.
Okay. Is this clear to everyone? Can I have some acknowledgements? Whoever is left alive, awake on the other side. All are alive? Okay. So yeah, that is this question basically. So if you understand this, try doing this and try doing these two. Okay. Shall we do more, or are you guys like you have had a lot of overload? Just let me know when to stop. Is it enough for today, or shall we do more? Nobody has any suggestions. Enough? What about others? Yeah, enough, right? Even I feel like if I were in your place, I wouldn't have, like I would have, it's already too much overload for today. Yeah, I know. So go back, watch the recording. I will make it a point to get it uploaded today itself, so that tomorrow morning when you get up, you have it available. So watch it again. Try these questions on your own. See how I am arriving at it logically. Think, always get into the mind of the person and see what he is thinking. That's important. Understanding a thing is important, but how you arrived at it is equally important. So try to stress on that always, and try to always come up with a recursive solution in level 1. Don't go level 2, level 3. It gets very messy. Then you will start making all types of whatever decision you have made, whatever recurrence, whatever sub problem you have defined, just stick to it. It will always be correct. If your formulation is correct, if you have not left out any case, or if it is correct, basically, then you will always be able to, the answer will always be right. You can, and sometimes you will be amazed at how it is right. And then when you draw a recursion tree, you will actually understand, oh, this is how it is unfolding. But you don't need to understand how it is unfolding when you are devising a solution, is all I'm trying to say. So try that. I have if you people who want questions, these are the questions. Try as much as you can. Try the permutations 2 question with the other 2. Try the combination sum 2, right? Combination sum question with the second decision. Today I told you another decision and another type of sub problem, right? We were looking at prefix, suffix, sub array so far. Today I told you another sub problem which was subsequences. And I told you like 3 ways of writing a recursive function. So just recapitulate everything. Not today. Go to sleep today. Do it tomorrow maybe with a fresh mind, and then we can resume from here. I guess we are good. We are well placed. We are well within our time to complete recursion within whatever time we have allotted. Okay, so I will then stay back for a couple of minutes for people who have questions. If you have anything you want to talk about, personal, professional, technical, non-technical, I'll just stay back for a couple of minutes and others can leave. Thank you for joining. Stay safe, stay indoors, sleep well, don't go out, and I will see you guys tomorrow. For people, I can take up some questions if you guys have anything.
Sir, in the cases like in the previous class, after you had put some questions, in the cases when we have multiple, like we have same elements in an vector, and we have to find the subsets which make the sum equal to the target.
That question we haven't discussed yet, right?
Yes, sir. But for that, we will need to remove the duplicates.
Yes.
Sir, okay, so we'll discuss it later.
No, you have any idea, you can let me know. It's a little tricky.
Sir, what idea I had was, first I got all the, like this is very long procedure. So first I got all the subsets in my a 2D vector. After that, I pushed the like the vectors one by one into a set.
Array. That's okay. So every time you insert, if it is already present, you will not insert it.
Yes, and from that set I
converted it back to a 2D array.
Yes, so this is a very long procedure.
Yeah, we will see better ways of doing it. Like that's one way, but that's not the recommended way of doing it. That takes up a lot of time also.
Yes.
There are, so if you really want to see whatever be it, always think about the decision that you are making. If your decision knows how to handle duplicates, then you will be fine. So think about how you can handle duplicates in your decision itself.
Okay.
So your decision is, let's say you are going ahead with the decision of the minimum, correct? So if your minimum can be, so then you will have to iterate over all unique numbers, correct?
Yeah.
That's it. If you iterate over all unique numbers in your decision, then you will be able to avoid duplicates.
Okay.
Do you understand what I'm trying to say? In the for loop of the body of the recursive step, if you remember that we coded today, we were just going blindly through all the elements from start to n minus 1, right? N minus 1. Instead of that, you will only go through them, those elements which are unique. You will go through them only once. Okay. So if you have already called the sub problem for 2, then the next time you encounter a 2, you don't call a sub problem. That's basically the idea. If you can do that, then you will not have duplicates, right? Because duplicates are typically that only. Okay. Do you understand somewhat?
Yes, sir. I'll try to see if we can. Otherwise, we're anyways going to cover it in the next class.
We'll cover it tomorrow. Not tomorrow. Let's see. Tomorrow, second half maybe.
Okay, sir. So this is like this series is DP and recursion and then DP in the same.
Not really DP in this lecture, like in this sequence of lectures. Just an intro to DP, wherein we will say what is DP or what we do in DP, but will not get into the details. So the the timeline has been prepared in such a way that you get enough time to digest all this and then come back for DP, because DP we will pick up straight away from here. So I have already given you ideas of problems and sub problems. In DP, it's nothing but you store the sub problems. That's it. So if you have an idea of the problems and sub problems, you will have an idea of how to store them, what kind of data structures to use to store them, and look them up, right? So that's, in that sense, DP will be a continuation of what we do today or in these sets of lectures.
Okay. Thank you.
But yeah, we will not be doing DP too much now. Any more questions? Anyone has any question? Anyone having any personal concerns, technical, non-technical, facing issues with preparing, coding? Feel free to speak now, or you can ping me later also. We can talk. If you want motivation, you are demotivated, anything, feel free to reach out to me. I would be more than happy to assist you. Okay, so I don't yeah, groups are decided just on the basis of diversity. So we have tried to include people of different colleges, different branches, different batches, DSP1, DSP2, DSP3 together into one group, like every group. So that's how we have decided the groups. But you are free to go to any group as long as you're fine. Captains, vice captains is again just there was like there is no one like metric for captains, vice captains. It's just that they are some people that the team feels that they might be able to execute it, or have time and availability. A lot of factors get into that. But if you want, no, it's not about better. See, there is no notion of better, good, better, bad here in DMARCs. So don't worry about it. Okay. You, if you want to volunteer for anything, you can let me know. It's perfectly fine. You want to become a captain of a team, we would be more than happy to do that. Nothing like it. If somebody comes forward and volunteers, we would do that. If you want to change your group, you can let us know. We will put you to whatever group you want to go. These are all voluntary things. It's just that to give you a head start or to give you some initial direction, we have done this. Otherwise, what we could have done is we could have told you to divide yourselves in groups and elect a captain, vice captain, which would have been like very unruly, right? So that's why we just gave you some initial direction, but nothing is stringent. There is no judgment that has gone in for any person. Generally, it does not happen for any case here at DMAX. Okay. For what? If you are looking for interview preparation, I don't think competitive programming and interview preparation are the same things. If you are only looking for getting a job in a good company, you should do lead code, interview bit, and hacker rank as much as possible, and not really code forces, or I mean they are. So yeah, lead code is the Bible. Look like the Bible. People do 300, 400, 500 questions on lead code before sitting for interviews. Yeah, in my opinion, 300 is enough. 200 is enough, but it should be across topics, all kinds of difficulties, medium, hard, easy as well. So then depends on the questions also. Okay. Anything else?
Sir, so like lead code or interview bit, like which one should we follow?
Yeah, interview bit is a little too difficult to start with. So if you are starting out or you have you are not, lead code would be a good place to start. Do easy medium questions on lead code. Pick up a topic, filter questions, easy medium, maybe some hard questions. Do them for that topic. The way you judge a question is when you open a question, there will be a number of upvotes and downvotes for a question. So generally questions which are good have far more number of upvotes compared to downvotes. You will see typically 2000, 3000 upvotes and 10, 20 downvotes for questions. Those are really the good questions on lead code. So try to do them first. And once you have some acquaintance with a particular topic, you can try interview bit. Like I did both. I completed interview bit and I did close to 400 questions of lead code. Like
For
in
your
a
internships or
no, I work for my placements, like when I was sitting for placements. So when I was sitting for placement, lead code had only 350 questions, I think. Now it has around 1200 questions. So I did all of them, and I did the entire interview bit in like 6 months or so.
okay, and sir, I have to appear for my internship exams in August. So, what should be the timeline? कि मतलब when should I start with interview bit or should I do side by side?
इंटर्नशिप इंटरव्यूज एग्जाम्स मतलब क्या इंटरव्यू होते हैं क्या?
हाँ सर, ऑन कैंपस एग्जाम्स होंगे पहले, फिर इंटरव्यूज अगर if you are selected in the coding round.
अगस्त तो अभी टाइम है में अच्छा है फिर तो मतलब सो यू हैव अ गुड अमाउंट ऑफ टाइम आई गेस यू आर इन अ गुड सिचुएशन इंटरव्यू बिट आप मे बी अभी लीड कोड कर लो एक आधा महीना आई वुड सजेस्ट अभी अप्रैल चल रहा है ना मई जून जुलाई या मे बी मे एंड you could do lead code as much as you can and side by side and then maybe 1 month you can spend on interview bit. I guess that should be enough, more than enough for internships. I guess it will be more than enough, but make sure your basics on CS fundamentals are also covered because companies ask that also, like in my college they do.
Okay sir.
Okay, so do all the DPPs. They are the questions are really hand picked. So some of them are classical questions, some of them are modifications of classical questions. So practice, you have to practice on your own. There is no denying the fact, but at least complete the DPPs because they have, like, those questions are classical problems which have been asked in the past frequently. So do that. And then, yeah, Sanskar, you have something? Right. Okay. No problem. Anything else? Ankit, her next round of mock interviews, you will get to know. The team decides that and not me. So you will get to know about it on WhatsApp. Yours got cancelled as in what happened? Like they cancelled it or you cancelled it? Okay. Yeah, I guess then you can tell them that when they open up slots. So when they open up slots, you can book one. Okay, okay. Interviews and availability. Yeah, so wait for some information. We'll definitely post something in the group. Okay. No problem. All right. Anything else from anyone? Oh, okay. All right. Then good night, guys. Take care. I will see you tomorrow again. I will end the meeting now.